Class 12 Mathematics, NCERT New Delhi and COHSEM Manipur. Unit 1 Relations and Functions. Exercise Miscellaneous Examples on Chapter 1. Question number 1. Let f be a function from R to R be defined as f of x equal to 10x plus 7. Find the function g from R to R such that gof equal to fog equal to ir. Piriba f have a function ama pirame g have a function ama putu gof equal to fog equal to ir ga manaba condition asibu chumba dugumba function g have ama putu haibane. We have fog haibasi ir ga manare. Fog ki definition panjalabadi fog of x equal to ir of x for all x belongs to R. Fog ki definition palagadi f of g of x ni ir of x habadi x ni I haibadi identity function ni. Identity function se I na kangnai on the set R da define tarogadi madubo ir na a da define tarogana I suffix a na kangnagani I of x the x tarani. G of x की value the f of something f x की 10x plus 7 ni the x2 is g x na sindu over the 10x plus 7 की x to g of x na sindu e mafam asidagi koine x to solve to g to solve to over the gx have c x minus 7 by 10 putokadaba function gx to sini. Question number 2. Let f be a function from the set of whole numbers to whole numbers. Be defined as f of n is n minus 1 if n is odd and f of n is equal to n plus 1 if n is even, so that f is invertible. Find the inverse of f where w is the set of all whole numbers. Piramiba function C w dagi w dani f haina kawi f of n gi value di n minus 1 oigani n odd oirabadi n plus 1 oigani if n asin even oirabadi. Hojik ahanbada function ji invertible oi ulu haibani. Invertible gi damakta di aikoina function ji 1 1 ahanbada utgani. Madugi damakta di let m and n belongs to w. Domain da leiba number ani khakni m amasung n is any two whole numbers ni domain gi. Case 1. When m and n both are odd animak odd number oirabadi, then f of m equal to f of n, as it implies m minus 1 odd number singidi 1 less ni odd number gidi 1 less m dagi amahan thaba n dagi amahan thaba. Hojik solve torabadi m equal to n. Case 2. When m and n both are even animak even oirabadi one more f of m equal to f of n gives m plus 1 equal to n plus 1. This gives m equal to n. Case 3. When m is odd and n is even, m na odd oiraga n even oiba matamdadi f of m equal to f of n gives odd number dadi 1 less m minus 1 n dadi n even oirabadi one more n plus 1. Odd number da 1 khaidokhradi even tarani. Even number da 1 hapsalabadi odd tarani. Asumna even ga odd kadi kaidongoi da sumanaroi. Thus m does not equal to n. Odd number ga even number ga manade makoi gi mami ani manadre. Case ahum segi koina kai loba yare. So f is 1 1 function. Ahan bagi case 1 1 unique solution phangi ani suba case ta su 1 1 unique solution phangi 1 1 oi ahum suba case su 1 1 gi case ni aduna case ahum makta case pumna makta function ji 1 1 oi the proof tore. Next on to amu proof toxi invertible gi dama on to wali let n belongs to w. Karamba w di yawna w ani sigma nung da ko domain da leiba any number amani n harisi. If n is odd, codomain da leiba number da odd orabadi, then n minus 1 is even. Odd number dagi whole number odd number dagi ama khaido obadi even orani and n minus 1 belongs to w. Domain da leiba n minus 1 si domain da leiba such that f of that n minus 1 is n minus 1 in even already one more, that is n minus 1 1 1 8 actually we get n. If n is even oirabadi domain da leba codomain da leba n number n has even oirabadi mangondagi 1 hapchilabadi odd oirani madugi 1 n plus 1 adusu whole number haibadi domain da yauba any number ama oirani such that f of n plus 1 odd number gidi 1 less ni n plus 1 dagi ama khaidokro n tare case anisina koida kari ule so f is onto as in picture masi picture di yengsi onto gi cases khatang lokalagi yengsi sida odd number ama lokalasi odd number da even odd aina mukanglok ani thona khaidokpa yai somdasu odd number hana laurasi even number hana laurasi 2 4 odd number amuk lokalasi 1 3 5 sida 2 yawan bayari sida 0 yawan bayari 2 gi yengsi 2 gi di 2 sine even oirabadi one more di 2 dagi 1 n is even ne even gi damakta di one more oigani if mahak na sida leirani 4 dagi di mahak su one more si orani sida 0 leiram labadi 0 dagi one more di sida leirani asumno 1 odd number 1 asigi damakta di 1 less 1 dagi amahan taba number di 0 ni 0 na sida leirani aduga 3 dagi 1 less di si leirani asumna 5 kusu 1 less di si leirani asida lawkiba cases asi sigi odd number 1 nji 1 hena khalasi 1 dagi ama khaido di 0 ni 0 haibasi whole number da yawi such that adu f of 0 di 0 plus 1 di 1 tai asumna 3 n na 3 loram labadi 3 dagi ama khaido di 2 ni 2 du whole number da yawi and f of 2 di 2 plus 1 di 3 phange hariba khida uliba cases to sige diagram sidagi kuni yamna line khange sima thus f is bijective and hence f is invertible bijective orabanina f is invertible ore hoji inverse ki ju ayek picture si lai ngai da khana horasi also f inverse habase abadi even na odd na even da sapani somna lebi even khuding ma ki somna odd lere even somna leba even khuding ma ki odd khuding ma ki even odd khuding ma ki even khuding ma ki odd also f inverse of n di n minus 1 n is odd wherever the odd makaina odd n odd wherever the odd tagi ama khaidokraga even tarani asumna n sin even wherever the even gidi 1 more that is n plus 1 are masidi kanagamane f of n gi definition doga chap manare adon f inverse of n di f n ga mane haibadi f inverse is f itself masi ojare hence proof. Question number 3. Let f be a function from R to R be defined as f of x equal to x square minus thrice x plus 2. Find f of x. Let's see f of x di kaya gamana kare x square minus thrice x plus 2 ni. Ado nauzi f of x ki x to bu quadratic expression asin mausuladi right lari x kudumaks to quadratic expression asin mausulasi we get x square x to the quadratic expression silo square minus 3x to the quadratic expression silo plus 2 Hoji expand to a minus b plus a plus b plus the whole square expansion to robadi I go na term 1 2 3 4 5 6 sig term sima phange mathang the 3 is the purity we get this plus 2 like term sim kunjalabadi kon expression si phange machine putokada ba f of x ki value duni. Question number 4. So that the function f from R to this interval, open interval, defined by f of x equal to x by 1 plus modulus x belongs to R is 1 and onto function. Variable function G 1 and onto O have ulu. Let us see on with the 1 uchi. Let x y belongs to R such that f of x equal to f of y. x amasung y haiba number anikak real number domain dagi number anikak laukhale makhoi gi mami x gi mami f of x ka y gi mami f of y ga manana loksile x amasung y di manai natraga manade pande. Case 1. When x y greater than equal to 0, x amasung y si 0 amasung 0 dagi chawba number singoirabadi, then f of x equal to f of y gives function value dauren modulus taparoi 0 amasung positive number sing absolute value di yaudaba expression duga chap manai. The cross multiply and solve, we get x equal to y phangani. Case 2. When x y both less than 0 habidi negative number singoirabadi, then f of x equal to f of y gives modulus of x ki minus x lani modulus of y di negative number ki modulus di minus y na negative or di ma ki modulus di minus y. Solve torba matam x y phange, unique solution phange. So f is 1 1. F as a 1 1 case animakta f si 1 1 ki nature oina phange. Mathangda on to katangare, let y y equal to f of x where y is the domain co-domain by any number amani. F of x when x is greater than or equal to 0 modulus yaubagini greater than or equal to x and case anithona khanarisi x na positive na traga 0 oirabadi, then y equal to x by 1 plus x si x asi modulus mangan khaba matung dani positive number amasung na traga 0 gi absolute makoi mak tagani. Cross multiply and solve x, we get y by 1 minus y asidi minus 1 zoloba yade 1 zoloba yade maramdi open interval minus 1 1 dagi any number amani. Hauji koina when x is less than 0 negative number orabadi y equal to x by 1 minus x tarani x ki modulus t minus x agani if x the negative orabadi. Chidigi su cross multiply taraga kon solve x equal to 1 y by 1 plus y na minus 1 oidrani makha 0 sungoi oidre. Case animakta gi khoina kari khange phangai bi x ki value singa si any real number ma tabanga mi y na open interval minus 1 1 dagi loning number amal lowrabasu, hence thus f is onto ori, hence f is 1 1 and onto, hence the result is proved. Question number 5. So that the function f from r to r given by f of x equal to x cube is injective. Piriba function is injective oi 1 1 oi ulu haibani. Let x and y belongs to r such that f of x equal to f of y. X amasung y domain di yaw by any two real numbers ni makhoi gi mami f of x ka f of y ga manana loksile. Then f of x ki value di x cube ni f of y ki function value di y cube ni. The transfer and factorize, we get this. Ahan ani suwa expression asi assume na factor se assume na ibaya masi di positive number ngaktani, positive number ki square positive ani thing positive tar cannot be 0 divide out of cross second factor na, we get x minus y equal to 0, x equal to y, unique solution phange masino 1 1 ni taksare, thus f is injective. Question number 6. Give examples of two functions f from n to n and g from z to z such that GOP is injective but g is not injective. F amasung n dagi n da g na z dagi z da asugumba function ani gi example piu GOP na injective oiba g na injective oidaba. Consider f of x is x identity function kawi fc g of x na modulus function kawi. Let us see. When x equal to f of x, f have a function na si husi aikoina f have a function si GOP x, let x equal to minus 1 y equal to 1 so that g of minus 1 g is injective oi di utkadari manadaba number ani laure, g of minus 1 gi meti minus 1 gi modulus ti 1 lare and g of 1 gi modulus ti 1 lare ani si manare. Premise x amasung y di manade aduga mami ani di manare masina karita a g is not injective, g injective oidre. First case sama ule. Next GOP yang si GOP si injective oi utsi 1 1 oi utsi. GOP of x di z of f of x ni z of f of x di identity function in x tarani z of x di modulus of x ni sima pangkre. Also GOP haibasi define tawgani GOP si karamba setagi setana n dagi sigi n asidagi sigi n asidagi sigi z asta lakpani n to z ni gob of x karamna define tawgre modulus x ni. Let xy belongs to n natural number ni such that gob of x ka gob of y ka mane hene loksile. Gob of x की definition adi z of f of x ka mane gob of y di z of f of y ka mane z asidi injective oide f of x di kaya ga manore f of x di x na sindokro f of y di y na sindokrani z of x ka z of y ga manare z of x di modulus x ni z of y di modulus y ni sidiki solve to di x equal to y x equal to minus y di invalid ni minus y have a c kuna oibi ya di x and y di natural number sini x equal to minus y is invalid x equal to y si bu khone kari kawi unique solution leba kawi. So gob is injective gob si injective oi have to koi utle. Question number 6 ka ani suba example. Roman number 2, let f of x equal to 5x and z of x equal to x square. Let x equal to minus 2 and y equal to 2. X amso y si manadaba number ani lowri. Then g of minus 2 di minus 2 square di 4 ni. Z of 2 square di 4 ni. Aduna minus 2. x ka y ka manade maram di minus 2 ka manadra mine x ka y ka manade mabani gi mami ani di z of x ka z of y ka manare masina karita is z is not injective z asi injective oide. For second case gob is from n to z ni gob have say n set gi sidagi z la function amani gob of x di kaya ka manare matanga sidadi z of f of x ka manai f of x di kaya ka mana hore 5x z of x the modulus x ka manai g of 5x the 5x whole square that is 25x square or let x and y belongs to n such that gob of x equal to gob of y injective y unanabagi damaktani huji koine x amso y natural number ani laukale mami mana halle gob of x the 25x square ni gob of y the 25y square ni solve to rabadi x equal to plus minus y x equal to y na chumani x equal to minus y is invalid. Natural number amaga atop ne ama negative number amaga positive amaga negative amaga de kaida wani sumana de masibu khoni unique solution leba kaure. So gob is injective gob se injective ore na question number 6 ki function ani lore madusu example ani dusu lore hence pro. Question number 7, give examples of two functions f from n to n and z from n to n such that gob is onto but f is not onto. Function ani low example ani pu f na n dagi n oiba z su n dagi n oiba gob na onto oiba f na onto oidaba. Consider f of x to x plus 1 z of x to na x minus 1 when x is greater than 1 when x equal to 1. Ahanbada koina huzik let f of x equal to x plus 1 laure function namana example da g of x na x minus 1 x greater than 1 when x is 1. Let y equal to f of x where y belongs to n for domain x belongs to n. X habasi yengasi f habasi koina karina utkadari se onto gi matang ni f si not onto oidi utkadari mi. Then y f of x the kaya gamana hore x plus 1 sidagi x to solve toro x equal to y minus 1 kari phange when y equal to 1 y no 1 or the x equal to 0 does not contain in n ore 0 sidi natural the yaude aduna y gi value ama kone lokalo bada magi premise to 0 the natural number the yaude. So f is not onto function f is onto function oidre gob is onto when n greater than 1 n 1 dagi chaurabadi n 1 dagi x no 1 dagi chaurabadi gob of x the z of f of x ni f of x the x plus 1 gamane g of x plus 1 1 dagi chauba number am the 1 hapsaladi madu 2 tare madu 2 su 1 dagi chaure the 1 dagi chauba number amagi x plus 1 of minus 1 that is x phange. Thus, gob is onto function. Gob as a onto function ore. Gob as a onto function ore. Ani suba example da let f of x equal to x plus 5 and z of x equal to x minus 5 x greater than 5 whose value is 5 when x is 5. Let's see, y equal to f of x belongs to n, or implies y equal to x for f of x the x plus 5 ni. X to solve to see y minus 5 fange. When y equal to 5, 5 is natural number number amani codomain da. Then x equal to 5, y the 5 is the 5 minus 5, that is 0, does not contain in n. So f is not onto function, f is onto function oidre. When x is greater than 5, x is greater than 5 to give oirabadi. Gob of x the g of f of x the x plus 5, g of x plus 5 the x plus 5 minus 5, that is x tare. Thus gob is onto function, gob is onto function or. Example animal pire proof sutor. Question number I. Given a non-empty set X, consider P of X, which is the set of all subsets of X. Power set of X है सुखंग नहीं. Px है बस set अमनी X है बस set चिके subset पूर्ण मक याव power set of X. Define the relation R in Px as follows. Relation नमक define तो जी Px है बस set असीदा. For subsets A, B in Px, A related to B if and only if A is subset of B. A and B is subset or A is related to B. Is R an equivalence relation on Px, P of X? Justify your answer. Equivalence oibra hangbani adudi huji ahan bada reflexive utsi. Reflexive ki damoktadi we note that every set is a subset of itself. Masana masagi subset ne habisima di koi khangle. Therefore, so for every A belongs to Px, A is subset of A. Wamasi mataki statement si symbolically asumna pongdo A implies A is related to A for all A belongs to P of X. Implies R is a reflexive relation on Px, P of X. Reflexive oikere matang da symmetric. Let A is related to B. Related or A is subset of B. Implies B is subset of A. Is false. Masih lal. A से B के subset नहीं, B से A के subset है वही लाल है. लाल बनी ना B is related to A is false. B के A के related वही है वैसे लाल है. लाल वही R is not symmetric. Symmetric वही रही. Case अमा मतंग the transitive. Let A is related to B, B is related to C. This gives A is subset of B, B is subset of C. Then automatically A is a subset of C. That is A is related to C. Implies R is transitive relation. Ahum sigi manungda reflexive ore, symmetric ore, transitive ore. Adudi. Hence R is not an equivalence relation. R is equivalence relation ore. Madu symmetric utpamatam the sort of conclusion P yare. Question number 9. Given a non-empty set X, consider the binary operation asterisk from Px into Px to Px. Given by A asterisk B is equal to A intersection B for all AB in Px, where Px is the power set of X, so that X is the identity element for this operation and X is the only invertible element in Px with respect to the operation asterisk. X है बसिना Px के identity binary operation से के identity element ni X कतंग invertible ओइगनी Px याव element पूर्ण मक्ता operation asterisk ता. First part, identity element. Let E be the identity element in Px with respect to X. Karigina capital E load the Px have a seed the element ponamok to set ngakani. Set single city icon capital letter single kangnai. Adan hosi capital E on a loader C. Then E have a identity element or any set E. Px the over any set A have a maga A asterisk E equal to E asterisk A do A tagadavan any set A se tagadavan. By definition of an identity element के मतुंगिना अदुदी A asterisk E की value दे क्या गमाने A asterisk B हरदी A intersection B गमाने A asterisk E हरदी A intersection E गमाने E asterisk A सु E intersection A गमाने equal to A for all A belong A subset of X S A से होगी S के subset और है A का E का intersection तोरा A तार है E ga A ga intersection tawra A tare adu rabadi hoji E have say X orani karam no oribano E has X orani hairagadi set adugi any set kudung maka ma X ki subset pumna maktu dagi subset pumna maktu kap amaga intersect tabu matamda intersect tabu matamda any set to tarabadi साइगे आइडेंटिटी एलिमेंट नि हाइना लौख्रिबा x की सबसेट से x सोइदन ओरन x का महा के एनी सबसेट का कथनरबदी एनी सेट तो तागने अदन e have से x ओरे सिन करी हारे thus x is the identity element with respect to asterisk on px x asi kaktane x na identity element of the binary operation asterisk on px ore second part let a be an invertible element of px px have a set asida px to the yaw element puna makti in invertible or element do in hana lorasi let s be its inverse s na mahaki inverse ne hana khalasi by definition of inverse na a asterisk s equal to s asterisk a equal to e that is what of the e value the x power x putting thamani a asterisk s the a intersection s kamane s asterisk a the s intersection a kamane x a ga a intersection s to x tarab s intersection a to x tarabadi s habisi kaya oigani a to s to loinamak x tarani habidi a c x ke subset ni s asisu s ke subset ni subset x की सबसेट any two subset की intersection do x tarabadi any two set ani do set के superset x to orani thus x is the only invertible element of px px the yawa element pumna maktagi x habisina invertible element sima kaktong oigani for asterisk and it is the inverse of itself s ki inverse the x masamak adum oir hence proof. Question number 10. Find the number of all two functions from the set 1, 2, 3 and to itself. Set masamakta n elements of a set amadigi masamakta oiba onto number of onto functions putu haibani. Number of onto functions putu haibani. Matang asida koi ama kitang nainaba yaba ama kaktang di. Set asida ki semba yaba sigi function ani sigi function kaya semba ya yeng si function mahak na map torugodo si wana sina map torugodo wana map torugodo element si wana obi b do obi c do obi mo ohum the map toroni tu na so amuk map torugodo element si tu na a da tu na b da tu na c da mag mo ohum yarani 3 na amuk map torubi yaba elements 3 na a da 3 na b da 3 na c da map torurani marks mo ohum da yare asumna 4 na map to yaba element masing si 4 na a da 4 na b da 4 na c da marks mo ohum da yare sidagi semba yaba number of functions te set ani sidagi semba yaba number of functions se number of functions kaya ore number of functions from a to b a dagi b de oiba function de 3 se mari rak purinarade 3 se mari rak purinarade choban number ama phange 3 power 4 phange sidi karina number of into functions number of into functions plus number of onto functions into function ga onto function ga ni sambar nani into function di kamaina puthokani into function di piriba diagram asigi matungina amuk hani yektoksi kon into function gi damakta di a set 6 the layer b set 6 the layer mark c 1 2 3 4 mark element a b c into function d number of into functions d mayam sina element into function d element sida asumna map to a da map to matamda a da mok b da mok c da mok mawong ahum ama lere mawong ahum ama tare amok su si sina amok element sida tabagi su element amamuk kaktamo exactly one image range ki element ama kaktada tabadi asumna amok su mawong mana mawong ama mawong ahum lerani ahum ani da tabadi number of ani da tabadi khona number of into functions the element ani exactly two image da tabadi two image da ani lokala ga semba function chida mayam ama leirani madugi mayam singdo sigi number ama khangani sigi number duna sigi number into function sina sigi khaidokna robadi ngasai gi 3 power 4 sigi khoina khaidodi on to function on to function di 3 power 4 dagi number of sigi b tare na khalasi b sigi b do khaidok khala number of into functions that is 3 power 4 dagi b ta kana sumno khot pi yagan. Here A consists of 1, 2, 3, 4, n, and n of A is consists of n elements. The number of onto functions f from A to A is npn, that is n factorial. From the n elements labas from the n elements labas from the same yaba number of onto functions n factorial. For question number 11. Let S consist of A, B, C, T consists of 1, 2, 3. Find F inverse of the following functions. F from S to T. S tagi T do oiba if it exists. F haiba S tagi T do oiba function asigi inverse put to U inverse level jaga sing do haibani. Ahan bada F Roman number 1 gi piri ba F asida A na 3 dani, B na 2 dani, C na 1 dani. Hariba function se 1 1 oibra invertible oibra hana yengsi. Any two order pairs of F have different second components. A3 gi su A3 gi any two order pairs log si ahan baga ni su lo second order pair second component 3 ga 2 manadi ahan baga ahum su baga lokal si second component O3 ga 1 ga manadi ani suba order pair ga ahum suba order pair ga lokal 2 ga 1 ga manadi aduna sidagi coin any two order pairs F to gi any two order pairs lokal ga second component manabra yengba matamna manadre badi. So F is 1 1 F is 1 1 ore. For range also range of F the second component simony 1 2 3 1 2 3 which is equal to T ki setu ga manare codomain of F ni range ka codomain ga manare badi function on to ore. So F is on to anima 1 1 so ore on to so ore, hence F is invertible and F inverse equal to A3 gidi 3A B2 gidi 2B C1 gidi 1C. First question number 1 proof. For Roman number 2, any two order pairs ani suba B1 siga C1 sikala khurmat second component manare B amasung C give same image pangabadi 1 1 oidre. Clearly F is not 1 1 as B1 and C1 have same second components. Makoi manaba components sing leramina 1 1 oidre. So F is not invertible. Invertible oidrabadi inverse putopa yadre. Hence proof. Question number 12. Consider the binary operation asterisk from R into R to R and O from R into R to R defined as asterisk B is equal to modulus of A minus B and A of B is equal to A for all AB belongs to R, so that asterisk is commutative but not associative. Asterisk haiba of binary operation is commutative or associative oide. O is associative but not commutative. O asina associative or adu commutative oide. Further, so that for all ABC belongs to R, A asterisk of B O C equal to A asterisk B O A asterisk B. If it is so, we said that the operation asterisk distributes over the operation O. Thus, O distribute over asterisk. Justify your answer. One by one, quick proof toxi. Function sing da piba function sing do table 9 assume ite first part akoina asterisk si commutative ki damakta di we have asterisk B is given as modulus of A minus B, which is again B minus A hanus EBI B minus A modulus, which is what B asterisk A. Asterisk B ga B asterisk A ga manarabadi, so asterisk is commutative. Asterisk commutative or associative being C asterisk of B asterisk C asterisk of B D modulus of A minus B ni number ani si amo asterisk C puthara si number asterisk ki nakan ani the level number ani si gi value outcome kya la kada ke modulus of first number, that is modulus of A minus B minus of second asterisk ki right level number na khai do ni si pange and A asterisk of B asterisk C di A asterisk puthara si B asterisk C di modulus of B minus C ni masi asterisk ki nakan ani the number ani lere definition policy modulus of first number minus second number asumna phangi right leriba ani se manadre aduna left leriba ani manadre so asterisk is not associative asterisk se associative oidre. Thus asterisk is commutative but not associative. Second part tari O is associative but not commutative ni. To show O is associative but not commutative, we have associative hana proof toksi AO BOC equal to BOC gidi right leba B tarani AO se putarani BOC gidi definition ge matung ina B tarani AOB gidi right leba A adum tarani asumna amuksu AOB OC equal to AOB gidi A tarani OC putarasi AOC ge right left leba A adum tarani right ani se manaradi left ani manare left ani se manarabadi O is associative. For commutative AOBD A tare and BOAD right left leba B tare A ga B ga manadramina right ani se manadramina left ani se manadrabadi so O is not commutative oidre O asi commutative oidre. Does O distribute over asterisk? Justify your answer. Third part A asterisk BOC equal to A asterisk putarasi BOC gidi right leriba B tarani A asterisk B gidi definition ge matungina modulus of A minus B orani amuksu right side A asterisk B O A asterisk C A asterisk B gidi modulus of A minus B lerani O putarasi A asterisk C gidi modulus of A minus C lere O gidi left leba number si tarani right ani se manarabanina left ani se manarabadi kona proof tore third part kama the fourth party AO B asterisk C AO putarasi B asterisk C di modulus of B minus C ni O gi definition ge matuna left leba A se tarani asumna AOB asterisk AOC equal to AOB gidi A tarani juga asterisk putara O AOC gidi A tarani A ge asterisk di modulus of A minus A di 0 tare right A ga 0 ga manadrabani na right ani manadre left ani su manararoi manadrabadi no O does not distribute over asterisk sigi manaramagadi O be holds distributive over asterisk haigadabani. Question number 13. Given a non-empty set X, let asterisk is Px into Px to Px be defined as asterisk B is a difference A minus B union B minus A. For all A, B belongs to Px. Px is a power set of the set XII. So that the empty set pi is the identity for the operation asterisk and all the elements A of Px are invertible with A inverse is A itself. Use this property. For any A belongs to Px, we have power set of X star yaw by any subset element ama A have amagi A asterisk pi D. Pi asi identity element ni proof togdrimi adudi A asina power set of S any element ni A asterisk pi sina identity empty space pi se identity element utkadabani A asterisk pi by definition di A minus pi union pi minus A minus pi have A intersection pi complement ga mane matang asida masima khangjing gadabani A minus pi have A intersection pi complement ga mane union pi minus A di pi intersection A complement ga mane pi complement di universal set U tarane pi ga any set ka intersection torabadi pi tarane A intersection UD always A have U gi subset ni A have U gi subset orabadi A tarani A ga pi gi union torabadi A tarani amuksu pi asterisk A putoksi definition of pi minus A union A minus U pi minus A CD pi intersection A gi complement union A minus pi di A intersection pi gi complement A gi complement pi ga any set ka intersection torabadi pi tarani union A intersection pi complement di union% set U tarani U orabadi A intersection U di kaya tare A intersection U di A tarani phi union A di A tare right ani manare therefore left ani se manare ba duga tare ba phone du su A or A for all A belongs to Px adu di phi se kari kaure phi have said thus phi is the identity element in Px for asterisk operation binary operation sigi phi sina identity element or next. For any A belongs to Px, we have A asterisk A is by definition A minus A union A minus A. A minus A di phi tare, A minus A so phi tare, phi ga phi ga union di phi tare. Sina ko kari ula A set any set amaga masama ka punjuma matanda phi tare, phi have a the identity element or horobani in Px ta. Do de by definition of identity and an inverse. So every element A of Px is invertible and A inverse is A itself. Hence proof. Let A consist of minus 1, 0, 1, 2, B consists of minus 4, minus 2, 0, 2, and f, z is are functions from A to B. B functions defined by f of x equal to x square minus x, x belongs to A, z of x equal to 2 times of modulus of x minus half minus 1, x belongs to A. R, F, and Z equal function nisi manabra hangbani. Justify your answer. Hint. One may note that two functions f from A to B and z from A to B such that f of A equal to z of A for all A belongs to A are called equal functions. Equal functions की definition makar hints pirame masi panjalaga function ani si manabra ullo haibani. Apiba singda sumne ito A. Now f have a sisu A degi B da f to the A the yaw element kayana A the yaw minus 1, 0, 1, 2 makoy ki function value putoksi f ki dasu f of minus 1 the f of x the x square minus x ni x square minus x ki the minus 1 square minus or minus 1 that is 2 pang f of 0 gisu putoni 0 square minus 0 the 0 tare f of 1 gisu 1 square minus 1 the 0 tare f of 2 gisu 2 square minus 2 the 2 tare hojik lai value se value marisima phange z gisu mo putoksi z gisu a degi b dani a the yaw element kudimaki z of putoksi z of minus 1 z gidi x the minus 1 pisilo simplify toroga 2 phange z of 0 gisu x the 0 pisilo x the 0 pisilo we get this 0 phange z of 1 gisu 0 phange z of 2 gisu 2 phange watak ta phangori ba value sing siga z gi phangi ba value same number sing gi phangi ba value sing manare haidi f of a f z of a ga manare. Thus f and z are equal functions. Ani is equal function or 16. Let A consist of 1, 2, 3. Then number of relations containing 1, 2 and 1, 3 which are reflexive and symmetric but not transitive is 1, 2 ne 1, 3 yawa reflexive ka symmetric oiraga transitive oitaba relation masingdu makhada 1, 2, 3, 4 piri achum makhallo haibani. Let us see. For reflexive oiba function o hingadabani relation o hingadabani for reflexive kidamakti we have to add a the element ahum sigi doublet ahum simi yaurani. Matanga for symmetric di 1, 2 yarum lovini 2, 1 half chillani 1, 3 yarum lovini na kona 3, 1 half chillani. We have found that 2, 1, 1, 3 hoji 1, 3 me yarum me kona 2, 1 am half chille ani si pyar sarasi 2, 1, 1, 3. These two gives uneasy transitivity skip to the 1, 1 skip to the 2, 3 letter which does not contain haribase hanagi 1, 2 ka 1, 3 ka hapsen kiba element manga siga amata sigi 2, 3 amata yaw ki matakta. Hence up to this we get one relation makoi sing si yauraga akoina element 1, 1 ne 2, 2 ne 3, 3 ne 2, 1 ne 3, 1 ne sigi manga simoga hanagi ani simoga yaw relation ama pange masi phawada. If we add the remaining two other pairs 2, 3 habamaga 3, 2 habamaga hapchalasi the resulting relations are transitive. 2, 3 do hapchal robadi mataki relation adu the 2, 3 hapchalu robadi transitive or transitive oidaba haibani aikona hapchalu the oidra 3, 2 hapchalu robasu 3, 2 hapchalu rehana mataki relation phangkibida ngari relation asida 3, 2 hapchilabadi symmetric oinabagi damakta 2, 3 lane 2, 3 la abadi transitive oigre aduna relation namata phangre. So there is only one relation resulting akombagi relation do ani hapsal kuma tam do oiba relation na do mata ki gul ahum che chendre reflexive symmetric oraga transitive oiba ngamdre transitive oi do when not transitive haramni na relation phangre so the correct answer d a asi ore there is only one relation ma ka establish to ngami. Let A consist of 1, 2, 3, then number of equivalence relations containing 1 to is 1 to yawa. A have a sin of 1 to 3 limit of yawi. We have R1 it was see reflexive equivalence ki damakta di reflexive order pair om si yawrani 1 to yawa haraga di symmetry on over 2 1 absolutely ani si combination na amuna 1 1 tie amuna 2 2 tie transitive so are symmetric so are reflexive so are ani suba relation am establish tawsi reflexive ki ahum japsal asi 1 to 2 1 japsal ani hanagi matak ta koin 1 3 absolute robadi symmetric oina ba 3 1 absolute ani aduna hoji 1 2 2 1 ga 1 3 ga pair semadi 2 3 pange 2 3 je amuk symmetric ohenge de 3 2 la ani r2 ani pange aduna the equivalence relation ani si a de gi semgot pa yabas ani si khaktang ni madu correct answer di b ore. Question number 18. Let f is a function from R to R be the signum function defined as f of x this, and z is from R to R be defined be the greatest integer function defined by z of x equal to x within tie bracket, where within x within tie bracket is greatest integer less than or equal to x, then thus fork and gop coincide in 0 1. Question number 18 gi yangsi period function do amana signum ni amana greatest integer function ni when x is between 0 to 1 including 1 fork of x the definition f of g of x ni g of x the x tar bracket ni x tar bracket se sigi 0 amasu 1 marakta leba number loksilu robadi 0 tarani f of 0 di kaya lani 0 0 tarani amuk f of dumale x no 1 laurubadi 1 tare 1 gidi x no 1 di greater than 0 ni 1 tare f of this gidi amuno 0 amuno 1 value ani phange adudi which is not defined must define tawdre. Also gop of x the z of f of x ni f of x the kaya gamane f of x to koina khane x the 0 amuso 1 gi marakta leba number ni the positive number gidi function value di 1 tarani g of 1 ni to 1 do third bracket ke manung de pisilu rabadi aikoina 1 gidi greatest integer function ni 1 tarani mathak ki jaga c siga hoji koi kari phange value manadre thus 4 ka gop ko ani manadre 4 ki value di gop ki value di 1 tare aduga 4 ki di value ani tare adudi ani si manabagi question hangwa yadre. So fork and gop do not define in 0 1 interval sida ani si define tawdre. Okay, number of binary operations on the set A, B, R. Sida siyamba yaba binary operation masing si kaya noi. The total number of binary operations on A, the end of A to the power end of A into A kisimpa purasi end of A di 2 ni to power 2 di C di 2 to end of A into end of A ni there is 16 tare. So answer is option B.